Hello! We are going to talk about gluconeogenesis. Overview. Gluconeogenesis is the process by which glucose is synthesized from smaller, simpler molecules such as lactate and pyruvate, while the catabolic linear pathway of glycolysis deals with the breakdown and extraction of energy from glucose. The anabolic process of gluconeogenesis.
Glucose is the major energy source for most tissues. Glucose can also be stored as glycogen or used for biosynthesis.
When there is a need for energy and other metabolic intermediates, pyruvate can be converted to acetyl-CoA. Clearly, the pathways that synthesize and break down glucose have to be carefully coordinated so that both are not turned on at the same time.
The major inputs come from the breakdown of amino acids and from lactate, produced by muscle tissues and transported to the liver by the bloodstream.
The formation of acetyl-CoA from pyruvate, catalyzed by the pyruvate dehydrogenase complex, is not reversible. The energy required for the reverse reaction is too great.
The 7 enzymes used in the glycolytic pathway are used in the reverse direction for gluconeogenesis. An examination of the bioenergetics of the irreversible reaction will show why different enzymes are required for gluconeogenesis at these points.
Pathway.
The seemingly simple process of converting pyruvate to phosphoenol pyruvate involves several steps, some in the matrix of mitochondria and others in the cytoplasm.
The first step in the gluconeogenesis pathway involves the conversion of the 3-carbon pyruvate to the 4-carbon intermediate.
Oxaloacetate cannot get out of the mitochondria directly, but first has to be converted to malate by the same malate dehydrogenase used in the TCA cycle.
Once in cytoplasm, the malate is reconverted to oxaloacetate, this time by a cytoplasmic form of malate dehydrogenase. Once in the cytoplasm, the malate is reconverted to oxaloacetate, this time by cytoplasmic form of malate dehydrogenase.
The second unique enzyme of gluconeogenesis, phosphoenol pyruvate carboxygenase, catalyzes the conversion of oxaloacetate to phosphoenol pyruvate. Note that this is another energy requiring step.
To review the conversion of pyruvate, the phosphoenol pyruvate requires energy input and carboxylation and decarboxylation steps.
Gluconeogenesis proceeds by simple reversal of the steps of glycolysis up to fructose 1,6-biphosphate.
At this point, reversal of the highly exergonic phosphofructokinase step of glycolysis is avoided by a simple phosphate cleavage.
Fructose 6-phosphate is then converted to glucose 6-phosphate by phosphoglucose isomerase. Then all that remains is to remove one phosphate group to generate glucose.
Control.
Control of gluconeogenesis occurs at two major points, at the pyruvate carboxylase step and at the fructose 1,6 biphosphatase step.
Created using Powtoon.